Greetings and good afternoon. Joining EECon 2021 again after having a brilliant keynote and 4 technical sessions in the morning. Now we have arrived for our second keynote for the day. In order to chair the second keynote of EECon 2021, I invite the General Chair of EECon 2021, Dr. Tusharo Ratnayake and Ms. Randima Hasanti. Please carry on.
Thank you. Good afternoon, everyone. It's a great pleasure for me to introduce the second keynote speaker today, who is going to talk us about power conversion technology for renewable energy systems integrated into medium voltage DC grids. So this is a topic in which we should all be deeply interested because in the future smart grid, it is a significant trend to integrate large capacity renewable energy into medium voltage DC grids. Also, this is a keynote collaboration with IEEE Power Electronics Society. So about our speaker, Professor Carlson is an associate professor at Tsinghua University, China. So he serves as an associate editor for IEEE actions on IEEE of emerging and selected topics in power electronics and Journal of Power Electronics. He is a distinguished lecturer of IEEE Power Electronics Society as well. Professor Sun also serves as PEL's Asia Pacific Regional Vice Chair, PEL's Beijing Chapter Chair, and PEL's Electronic Power Grid Systems Technical Committee Secretary. He received EE, ME, and PhD degrees in electrical engineering from Tsinghua University in 2002, 2016, respectively. His research interests include power electronics for renewable generation systems, microgrids, and energy internet. He was a recipient of Delta Young Scholar Award in 2013, Young Award of China Power Supply Society in 2017, IEEE Transactions on Power Electronics Outstanding Reviewers Award in 2019. So without further extension, let's welcome Professor Sun. So Professor, over to you.
Okay, sure. So, hello, and can everyone see my screen? See the slides?
Yes, we can see.
Yes.
Okay, thank you. Okay, and good afternoon, and all attendees of the conference and EECon 2021. And so it's my great honor to give the keynote. So, and as introduced by the conference chair, and my topic is the power conversion technology for renewable energy systems integrated into medium voltage DC grids. So, before my presentations, please allow me to give a brief introductions to our university and department. So, I'm from the Tsinghua University, and our university was established in 1911, and just in this year we celebrate 110-year anniversaries of our university. And we are located in Beijing, the capital of China, and also we are the top university in China. And currently we have 21 schools and 59 departments with faculties in science, engineering, humanities, medicines, economics, and management and arts. And for students, and totally we have 53,000 students, including the 19 master students and 17,000 PhD students. So in the spirit of Tsinghua is actions are always better than words. So my department, so I'm from the Department of Electrical Engineering, and our department was established in 1932 and ranking #1 in electrical engineering in China. And we covers almost all related areas in the field of electrical engineering, including the power systems, transmission technologies, power electronics and the electric machine systems, high voltage and the electric series. So, and I'm from the Institute of Power Electronics and Electrical Machine Systems. So, and currently we have 105 faculty members, including the 37 professors. And for students, we have almost 1,000 students, including the 500 undergraduate and 500 graduate students. So my own research focused on the power electronics for renewable, including the AC/DC, DC/DC, and DC/AC converters for the PV generation, wind generations, and fuel cell and battery energy storage, electric vehicle charging, and the interfacing converters in the hybrid AC/DC microgrids. Okay, so let's get into the main topic of today, and I will follow the following 4 parts: the background, the overview of DC integration technologies for PV and wind generations, and also we have proposed some novel solutions for the PV generation integrated into the medium voltage DC grid, and finally a summary. Okay, for the background, as we know, in recent years, the DC technology has become a very important trend in smart grid, especially the voltage source converter HVDC, also called HVDC Lite. You know, just in about 130 years ago, we know it's an AC and versus DC war by Tesla and Edison. But finally, in Tesla win this war because if we use the AC, we can transmit the power, electrical power, with very long distance. But for DC, it's very difficult. But in the past 3 decades, we have the power electronics technologies, so we can realize the high voltage to transmission. So here we have some data. Just in the year 2012 and 2017, and the 20 projects have been put into operations worldwide, with the total capacity reaching about 15 gigawatts. And also US already have 3 VSC HVDC projects on operations and planning more than 40 before 2025. Europe has already 13 VSC HVDC projects on operations and planning more 50 for 2025. So in China has 4 VSC HVDC projects on operations, including 1 gigawatt back-to-back connect between the 2 grid sections in the South China. So you know, we have the conventional and utility grid is in AC systems, but if we have this back-to-back DC converters to connect the 2 AC grid, will be the most suitable solutions for the future urban grid in the distribution network. Because this is a hybrid AC/DC distribution network can accommodate distributed DC supplies. We have more and more DC supply, PV, batteries, and DC load, just like in the electric vehicles, LED, and the drive lamp. Also, and if we have these AC-DC hybrid systems, we can reduce the conversion loss and the electricity and direct from the DC power supply to the DC load. And also, this hybrid system can provide the reactive power slot for the utility grid. Also enhance the reliabilities and the equipment. So just in recent years, the research and development activities of DC distribution networks has already conducted. And here show the Aachen University in Germany. They have key equipments in the medium volt DC distribution. Also in China, and the utility grid companies in South China has built the first emulation lab for the full DC distribution network in the year 2015. Also in Beijing, and we have the demonstrations project of multi-energy systems. So we just connect the different DC the distribution AC sections and interconnect by the medium voltage DC bus. So if we have this interlinking and by the DC bus, so we can enhance the equipment utilization rate and reduce the investment on substations. Because if one substations or one sections has fault, so other sections, other substations can provide the active and reactive power through this link. So we can reduce the outage time from the few minutes to an also, we can extend it to a medium voltage DC distribution network to integrate more renewable energy. Also, just say that in China, and a new project has already completed in this year. It's a 500 kV, 3 gigawatts DC grid project. Integrated the wind and the PV in the North China. So we think in the futures the large capacity renewable generations will be integrated into the DC grid. So we think the development of hybrid AC-DC distribution network and the large capacity renewable energy integrations are the two major challenges for the smart grid in future. And the distributed PV and energy storage systems for the MVDC distribution network will be an effective solutions. Because for these systems, they have some advantages. First is capacities. So if we increase the voltage from the low voltage to the medium voltage, so we can have the higher voltage integrations, which means enable the larger capacities. Also efficiencies, because if we have this in the medium voltage, so we can reduce the power conversion stage and the power losses. Also flexibilities, the power flow support from the PV energy storage can be used for the utility grid. And coordinations of PV and energy restrain the negative impacts of intermittent natures of PV. Okay, next I will give an overview of DC and integration technologies for photovoltaic generations and wind generations. Okay, so first let's look at the challenges and solutions for the large capacity PV generation system integration into the MVDC distribution networks. In this system, they have some key technical issues. First is the local and global MPPT problems. Because we just use the PV as the power supply, so we need to realize the local MPPT for the each PV panels and the global MPPT for the whole PV arrays. And also we have to deal with the distributed intermittent natures of PV. So it's not very stable. So it relies on the radiations and the temperatures. And also we have to realize the high power. High power here means the power rating is greater than 1 megawatts and very high step to deal with these key issues. We have some main technical challenges. First, we are lack of the ultra high step up, high power, high frequency transformers. Because in this DC-DC converters, we need the high frequency, high power transformers to realize the high step up in the power conversions and also the isolations for safety. And also the power device, the rating is very limited. If we use the silicon IGBT, the maximum voltage rating is 6.5 kV. But you know, we have the medium voltage and DC grid is 30 kV. So we need multiple power semiconductor devices to operate in series to fulfill these high voltage requirements. How to deal with these problems, these technical issues. So first for the local and the global MPPT, we can controlling the PV panels to achieve the string level or panel level MPPT and by the DC-DC converters. And for the distributed intermittent natures, we need to coordinations with the energy storage. Also, for the high power, ultra high step up DC-DC conversions, and we need to use the series connections of converter modules to reduce the required step up conversion ratio. And also we need to develop some novel DC-DC converter topologies and lower the voltage stress for each converter module. So we have proposed this in two-stage solutions. So in the first stage, we need to use the distributed DC-DC converters to control the PV panels to realize the low. Now in the back stage, so we need to use the centralized high power, high step up DC-DC converters and to realize the 40 to 80 times and the step up power conversions. So next, I use the predict for the first stage and stage. For the first stage, we use a differential power processing approach to realize the MPPT for each PV panels. Also, we can use the DC-DC converters and for each PV panels and the output series connections or the output parallel connections. Sorry, just disconnected. I will share again. Hello, and excuse me, and can you see my slide?
Yes, we can see, Professor.
Okay, so I will continue the presentation from this slide. Thank you. Just now I mentioned, and we have three solutions for the front stage: the differential power processing, output series, and output parallel. First, for this differential power processing, and we know as the series connected panels has the same in the current, so we need to use the additional circuit and to compensate the current difference and achieve the MPPT for each panels. And also, to realize the differential power processing, we have two methods. One is cascaded, the other is parallel. For cascaded and differential power processing, and the PV regulations, the power regulations only between the adjacent panels, and we can use the very simple converter topologies with soft switchings. So it's suitable for the series connected PV panels with smaller difference on their MPPs. So another is parallel DPP, and in this method, it compensates the PV panels from DC bus, and the precise panel MPPT cannot be guaranteed under the uniform compensations. So it's suitable for the series connected PV panels with larger difference on their MPPs. The other independent water for each PV panels, also with the output series connections. So this solution has some drawbacks because for the differential power processing, only part of the PV power processed. But in these solutions, all the powers, full power is processed, which limit the efficiency of converter. The independent MPP converters and for all the PV panels, and also the parallel. The full power process, the efficiency is lower. So, we have compared these three solutions. We found, all of these three solutions can realize the MPPT for the PV panels, but overall, the partial power transfers and only required in these DPP solutions. So the high efficiency can be achieved, but the main challenge is the complicated control and the instabilities. Okay, next I will introduce the backstage solutions. So in the backstage, we can use the centralized step-up conversions. In this, centralized DC-DC converters, if we only use one converter modules, it cannot fulfill the high voltage requirements. So we have to use the input power, it's IPO structures. And for these IPOI structures, it has some advantages, just like in the modular converter designs, the parallel connections at the input to achieve the high current, the series connections at the output to achieve the high voltage, and only small or the medium power transfer is needed. And also the IPOS can realize the automatically voltage balancing. So here show the converter module, the topologies. So we can use this full bridge as one converter modules, or use this boost plus full bridge and for the converter module. So here show an prototype. This is developed by our colleagues in the Institute of Electrical Engineering, Chinese Academy of Science. This just completed 5 years ago using the silicon IGBT. The input voltage 100 to 800 volt. The output voltage is minus plus 10 kV, 95%. and the power rating is 200 kilowatts. So later I will introduce our recent work, and it used the silicon carbide device and has a very high efficiency. And the IPOS is a basic topologies. In order to realize the IPOS structures, we also have different solutions. The first is we call it a parallel distributed series. It means we can use the interleaved boost converter and the LLC converters to form a super modules, and the interleaved structures reduce the inductance and the current demand of a single inductors to formulate to form this IPOS systems. So, and the second solutions is yes. The parallel and distributed series PPDS. So in this sense, you can use the voltage source converter module converters and PV arrays to switching AC voltage with the low frequency components, and also using the low frequency transformers and rectifier, and also to have the high voltage output. So we have compared these three solutions for the backstage. And for the hardware cost, the PDDS is greater than the PPDS and the PDSR. But the efficiency is different. The overall efficiency, the maximum efficiency is from the PDDS. So, and we have this in the overall comparison and the backstage, the PDDS, PDSR, and the PPDS. So we found then the PDDS and the PDSR and will be the suitable solutions for the backstage. Okay, so next I will introduce and the DC integration technologies of the offshore wind farms. Just now, I just introduced the technologies and for the PV integrations. Here, I just introduced the technologies for the wind farm integrations. So in the farm out wind turbines and the voltage. So first, we need to use the AC-DC converters and also the DC-AC converters, and to transform the unstable and wind power to the unstable AC voltage. And also, in order to integrate the offshore wind farms, the wind generators, and we have different approach. The first is the AC systems. All the transmissions are realized by AC. So we can see the transformers and the filters are very bulky, and so the HVAC transmissions is high cost and high loss. Also, another way is we can use this hybrid AC-DC systems. And it means at the supply side, we use the AC technologies, AC transformers to step up. And if have mid voltage AC bus, also using the high voltage AC-DC rectifiers and convert to the HVDC and transmissions. So these HVDC transmissions has a lower price and lower loss for long distance. And then these DC systems brings some advantages for the offshore wind farms. First, stability of And the second is easy of converter designs as a result of transformation ratio required, and also enhance the fault read-through capabilities due to they have the two stage between the grid and the wind turbines. Okay, and we also have some detailed integration technologies for the wind turbines and connections. So, and for each wind turbines, the power is not, but we need to connect the multiple wind turbines. So the wind turbines can be connected in parallel. And if we have these solutions, the voltage levels can be chosen freely for the DC link in the turbines and the internal DC connections, collection grid and the HVDC link. The DC-DC converters of each stage is optional. And also the transformer for one wind turbine has reduced the efficiency compared to large components. So the solutions with just one DC-DC converter towards the HVDC link has the lowest losses. Also, and another way is the wind turbines can be connected in series. And this has the advantages of the DC-DC converters towards the HVDC link is not required, but the disadvantages are also obvious. The high potential present in the wind turbines and the output voltage for the turbines must be overrated in case of the loss of a turbine. Also, in order to connect the wind turbines, so we need to investigate the converter topologies, and for the converters, first we need to consider fully converter and realize the full control operations of the turbine and smooth the torque control. And the uncontrollable converters cannot directly control the wind turbine torque, and there's a large torque ripples. So, and we can see the topologies for the controllable isolated converters. So here is a AC in the space A to C. This is the full with the high frequency medium frequency transformers. So here is another and controllable topology. Here shows the uncontrollable isolated converters. This is the rectifier and bias. And this is the three-level inverters with isolations transformer. Also, we can have some DAB, dual active bridge. This can also be used for the wind integrations. So when the input voltage of DAB does not match the output voltage, so a large reactive power circulating current will be generated. So this should be considered in the design and operations of the converters. Also, and we can use the uncontrollable non-isolated converters. First, the switching device on the input side of the DC-DC resonance converters are with that voltage. Also, we have some topologies, and topologies achieve the very high step-up ratios, but it's difficult to apply them to the occasions when the input voltage changes very greatly. And here shows the isolated modular multi-level converter and based MMC-based DC-DC topologies. And so we can see we can use the half bridge or full bridge or clamped dual submodules. The advantages of half bridge submodules is that the number of IGBT is lower, so the power loss is low, but then there's no DC fault isolation capabilities. But if we use the full bridge and the clamped dual submodules, this have the DC side fault isolation capabilities, and but it use small IGBT device, increase the cost. Also, and we can use this in the alternative active converters AAC. So for this AAC, the advantages is that it has a very strong DC fault isolation capabilities. The disadvantages is that it brings about the voltage equalization problems for switching device in series. Also, in this in the AAC and can be used without transformers. This for the non-isolation solutions. Without the transformer boost, the converter cannot achieve the high step-up ratios and does not have the electrical isolation capabilities, but can use in some outer asset. Or it show the auto transformer DC converters. So in the for solutions, the high voltage, low voltage side and share a part of the bridge arms and allowing a part of the DC current to flow directly from the to the output side. So while the AC side is still connections through transformers. And the advantages of these solutions is that the high and low voltage side share a part of the bridge arms, so which reduce the number of submodules and the capacity of the transformers and lower the cost. Also, we can use this in the multi-phase submodule cascaded. It's necessary to construct an AC loop to transfer the energy between the upper and lower bridge arms so as to maintain the power balance for the upper and lower bridge arms. The advantages is that the transformer is completely discarded and the size reduced and the capacity can be very large. Okay, and next I will introduce in our own work. We have proposed some novel solutions for the distributed PV generations integrated into the MVDC grid. And the output port, but they have a third port, and we call this the intermediate and the DC bus port. It means, and if all of this and TPC, this three-port motors have connected to the different PV panels, but the PV panels they have different maximum power point. So if one the PV power has the higher output powers than other in the PV panels, so the part of the PV powers can be transferred to the other modules, converter modules, through this intermediate DC bus, and also to maintain the power balance and the voltage balance for all the output voltage and as a output side. So the features is basically is based on the IPY structures, and the input terminals are connected with the independent PV strings to realize the distributed MPPT, and the intermediate DC bus act as a power exchange stations and benefits the modular converter design and output voltage balancing. So in the upper figure show the topology of the modular three-port converters, and actually these converters is a combination of two conventional converters, and from the PV to the intermediate DC bus is an interleaved buck boost bidirectional DC-DC converters, and also from the intermediate DC bus to the output side is a full bridge and the semi-active rectifier converters. So we just to combine these two converter topologies and to form this the modular TPC, by reduce the two sets of booster switch by sharing the active switches. Also, for these topologies, because the interleaved topology and most power is transferred, while only a minor part of transferred and through the intermediate DC bus. So this reduces the converter stage and enhance the efficiencies. And also, all the active switches can be operated with DVS in a very wide power range. So for control of the converters, result. It's a matter of just operation will form. Here show the tested results of the TPC-based the PV integration systems. We can find the MPPT for all the PV panels have been achieved, and the output voltage of all the PV all the converters modules are balanced even under the input power changes. And also we can see the both in the steady state and dynamic state, the voltage of all the converter modules is very good performance. Just now, and this in the 3-port converter-based PV systems, it mainly used for the voltage with the systems and with very not very high voltage, because and if high voltage stations difficult to realize, and we have proposed a high power, high voltage DC converters for the PV generations integrated into the MVDC grid. So in this application scenario, the main challenge is in MVDC integrations of PV generations, we need the high step-up ratios and DC-DC converters, and also we need the very wide voltage range PV arrays. We need to use the high efficiency DC-DC converters. So we have proposed new topologies, and this new topology is a coordination of a 2-stage, and the front stage is the interleaved booster converters, and also in the back stage is the RLC converter with soft switchings. So in the for the RLC converters, we can find the relationship between the gain, efficiency, and working conditions. And we can see if the RLC converters and working at the resonance frequency, so and it can achieve and the soft switchings with very high efficiencies. So and typically the RLC always operate in an open loop with just similar as the DC transformers, and without the voltage regulations. The intermediate DC bus voltage fluctuates slightly, and the adjust the voltage PV panels to realize the MPPT floating. This is floating bus technologies, so we can achieve a very high efficiency of the converters. The totally and the 2-stage converter efficiency is 98.59%. We can find the conversion efficiency increase by 0.6% compared with the fixed DC bus voltage. Now here shows the experimental prototype and the test results. And we have developed the with and the output voltage TV, and the maximum conversion efficiency is 98.59%, and the power density is also very high. It's over 1.5 volt centimeter cube. And for this and high power DC-DC converter designs, we have an optimized design of high frequency transformers. And also we have some optimal design for the passive components, just like the capacitors, inductors, and the bus bar. So and we realize this in the very high power densities is over 1.5 volt per centimeter cube. Okay. And finally, and I will give summaries of my presentations. So first, in these presentations, and we have given review of the PV generations integrated into the medium voltage DC grid. So in the development of smart grid, we think is a very important technical way to integrate distributed PV and offshore wind farms into the medium volt DC, MVDC distribution networks. And also in the PV generation systems integrated into the DC grid, the differential power processing DPP can be employed to realize the panel level and string level MPPT, while the IPOI structures, input parallel output series structures, is suitable to achieve the high step up conversions. This haven't reviewed the integration technique to the DC grid. The solutions of DC systems for offshore wind farms improve the power density and reduce the cost and loss for the long distance transmissions. And the key converters in the DC wind farms all work in the high voltage and high power environments. So MMC and the modular multi-level converters, MMC is necessary choice. At the same time, the realizations of high-power DC converters also rely on the technical breakthroughs in medium-frequency transformers. Circuits. And also, we have developed the high power, high voltage PV DC-DC converters, and novel modular two-stage proposed for the DC integration of PV regions. Features of high voltage, large capacities, wide input range, and high frequency isolations and high step-up ratios. And also with the coordination control of the two-stage converters, the converter achieves a very high power efficiencies. And design of high frequency and high power density is realized on an 80 kilowatts 5 kV prototype. Okay, and thank you very much. And this is my presentation today. And thank you for all your attendance. And I wish a great success of the conference EECon 2021. Okay, and I think I just finished on time, and we can have 10 or more 10 minutes to some questions or comments. Thank you.
Thank you very much, Professor Kai-san. So now the floor is open for questions. So audience, you can ask questions directly from the speaker, or you can put it on the chat.
Thank you, Professor Kai-sun. It's a very informative and very detailed presentation. You made a very good showing us the overview of the present status and showing the future direction towards the integration of medium voltage level power renewable sources to DC grid. Thank you very much at the persistence for this. And considering the level of power that we are handling, which is a reasonably large level of power, what kind of frequencies are you employing in the DC-DC conversion and this intermediate transformers DC-DC converter system inside?
So, and excuse me, and I think maybe due to the internet and connections, and I cannot get your questions clearly. So, and could you just put your questions in the chat box of the Zoom meeting?
Sure, I'll do it.
Okay. And also, I think today
Yes,
the
I'm
time is
writing.
limit. Okay. Okay. So not see the question in the chat box in the chat. Oh yes, here. So dual and DC supply to the yes network as well. MVDC. Okay. Oh yes, and sure, and in the for the RVDC network, and we have already the similar technologies, but in the technical challenges is not very high because in the RVDC grid. So we have the mature technologies for the DC converters, and also we can use the soft switchings to realize the soft switching to realize the high efficiency and the power and our efficiency and the very high productivity in the RVDC grid. It's much more easier than the MVDC. As I mentioned in my presentations, in the MVDC medium voltage, the isolations in the high voltage insulation technologies, and it's very important. And especially for the high frequency transformers. So we are doing some research on the new materials and the new topologies, and to realize the high power in the medium voltage and DC converters. And also in RVDC is much more okay, so I think the question is switching frequency in the DC-DC converters. Okay, and in our research, and as I introduced, and we have the two. We have two stages. The first stage is the non-isolated boost, interleave boost. The frequency is 50 kilohertz. And also for the backstage, we use the LRC resonance converter. The frequency, the operating frequency is 150 kilohertz. Because we use a silicon carbide device, so that it can be used in the frequency range over 100 kilohertz. Thank you.
Thank you.
Any other questions?
I'm typing one.
Okay, then I would like to thank Professor Kai-san.
One question is being typed for the presenter to see.
So it is already in the question you asked.
One more question, please.
Okay.
Okay. For the
one more question. So I put in the chat box for the ease of reading.
Okay. Okay. I find this quite what special strategy are you adopted to reduce the switching? Oh, okay. Okay, yes, and so we think the main technologies and for the switching power loss and is we just use the high volt silicon carbide power device. The silicon carbide MOSFET is very important to reduce the switching power loss because the silicon carbide has the better and also the performance and the very short the transient and compared with the silicon IGBT. And this is the first we use the silicon carbide device. And also we have developed some faster speed, the high speed for the silicon carbide MOSFET, because if we realize the high frequency operation of silicon carbide MOSFET, we have to keep the device just to turn on and turn off in very faster and without oscillations. And also during the operations, they have some high frequency and oscillations, some interference. So we need to reduce to restrain the oscillations. So we have developed some the high-speed gate drivers, and especially designed to restrain the oscillations in the high frequency operation of silicon carbide device. So, and also just if you have interested, and I can share my slides after the conference, yes, to the conference chair and Dr. Sushala and Resnayaka. Okay.
Thank you, Professor Kaisan. Thank you.
Thank you. There is another question, Professor. What is the frequency of the high frequency transformer used, and what are the determinant factors for the selection?
Okay. What's the frequency of the high frequency and transformer used, and what are the determinant factors for selections? Okay. Yes, and in our work, in the high power DC converters, and we use the frequency is 150 kilohertz. Why we use this frequency? We have considered the voltage gain, yes, and also the resonance frequency and of the converters, and also if we have the very high and the frequency, it will it can also to reduce the size, but it will bring some other design issues, just like the operations, some oscillations. So but if we use the lower, if we use the frequency lower than 100 kilohertz, so the size will be, yes, of the frequency. So we finally we have choose a trade-off of the different factors, and we think the determined factor is the voltage gain and the resonance frequency of the RLC converters, because this high frequency transformer is the key elements in the RLC converters. Okay, thank you. That's my answer.
Thank you. Another question here, I think you can see.
So
That's not a question.
The pair, and so I just because now in China we just 5:30, and I have to pick up my kids from the school. So I hope we can finish the session.
Okay. Okay. Sure. So.
It's okay.
Could you give me 2 minutes to thank you? Then we will finish the session.
Okay, thank you very much. Also, I will be very glad to join this conference, and also welcome the further questions and comments. And you can email me, and also looking forward to the more future and communications and collaborations with.
Thank you very much. Okay, so thank you very much, Professor Kai-san, for your valuable speech today on our conference. So it is our great honor to have you into EECon 2021 conference to deliver keynote as an IEEE distinguished lecturer. I believe that it's really a valuable topic for the audience. I am really delighted with your speech and your skills in clearly explaining about the power conversion technologies in renewable systems. So I once again would like to thank you for spending your valuable time by delivering such a worthy speech, and hope to get chance to hear more on the field from you in future also. Also, I would be grateful to the audience for your valuable presence and active engagement by asking questions. And also, I would be grateful to Ms. Randima Hasanti for coordinating the keynote speech as a collaborative event of Power Electronic Society. And also to the EESoc members for your numerous support by preparing and sharing flyer and all the technical support during the keynote session. So finally, I invite you all to the workshop on soft robotics for biomedical applications after this session that will start at 3:15 p.m. Thank you very much.
Thank you, madam. Before we move on, shall we take a photograph together as a group to commemorate the second keynote? If it's possible to turn on the video, it would be great. Okay, then we will take the photograph. Okay. Thank you everyone for posing for the photograph, and let's move on with our agenda. Next up, we have the workshop on soft robotics for biomedical applications. But before we move on, let's have a short break and come back to this same exact link by 3:15 p.m. The process will be held in this same Zoom meeting. See you all at 3:15.